Welcome back to The Explainer. I am so incredibly excited about today's topic. Okay, let's just dive right into this. Have you ever stopped and wondered exactly how computers manage to solve basically impossible math problems? I'm not talking about the easy ones, but those messy, massively complex area calculations that bring traditional calculus to a complete, screeching halt. Well, today, we're going on a geometric journey. We are going to see exactly how computer algorithms use surprisingly simple visual shapes to crack the code of numerical integration. Here's our roadmap for the explainer today. We'll start with number 1, the theory of the perfect rectangle, see what happens when math gets stuck, and then trace the computer's actual upgrade path, from basic lines and trapezoids right up to a massive parabolic upgrade, a real-world speed test, and finally, the boss-level optimization known as Gaussian quadrature.
All right, let's kick things off with section 1, the perfect rectangle. Because to really get this, we need to anchor some pretty complex math in a super visual, foundational concept.
Now, to understand how computers estimate area, we kind of have to understand the theoretical ideal first. There's this thing called the mean value theorem for integrals, and basically it guarantees that for any continuous wavy curve over a specific space, there is theoretically an exact perfect average height. If you could just find that one perfect height, you could literally flatten out all the peaks and valleys of the curve into a single, perfectly flat rectangle. And the area of that rectangle? It would exactly equal the true area under the curve. You can actually see how this works right here. Under that curve, the function f of x, we've got a shaded gray box acting as our perfect rectangle. Its top flat edge represents the exact average value of the entire function. It is a beautiful, deeply elegant theory. But, of course, there's a catch. Finding that perfect average height requires us to analytically solve the integral first. And that brings us perfectly to section 2, when math gets stuck. Because we have to confront some very real analytic limitations.
So what happens if we just can't find that exact area analytically? Because in the real world, functions don't always play nicely. Sometimes finding the exact antiderivative, the clean, analytical solution is just incredibly difficult. And sometimes, like with functions such as the exponential of negative x squared, it is mathematically impossible to express the antiderivative using standard functions. Our theoretical, beautiful, perfect rectangle is completely useless if we can't actually calculate its height. So how do we get around this giant mathematical roadblock?
We use workarounds. Welcome to section 3, lines and trapezoids. This is where numerical integration totally comes to the rescue. Since we can't build one giant perfect rectangle, computers do the next best thing. They chop the entire area up into tiny, manageable pieces. We usually start with simple rectangular chunks, but honestly, those are pretty clunky. So, step 2 is an upgrade. Trapezoids. Here, we basically draw a straight slanted line connecting the two top endpoints of a tiny chunk of the curve. By summing up the areas of thousands of these tiny trapezoids, we can estimate the total overall area. But here is the inherent problem with that approach: the error gap. A straight line is rigid, right? But a curve is curvy. When you use straight-edge shapes like trapezoids, you are physically leaving little slivers of empty space. Or maybe you're accidentally including extra space right outside the curve. This physical gap is what we call mathematical error. To make that error smaller with trapezoids, you literally have to chop the curve into millions of unimaginably tiny pieces. And yes, it works, but computationally speaking, it's just pure brute force. We really need a smarter way to hug the curve. Which leads us directly to section 4, the parabolic upgrade. This is where the geometric evolution really takes off. Enter Simpson's rule. Instead of fighting the curve with rigid straight lines, Simpson's rule actually works with the curve's natural shape. But there are a couple of strict rules to this upgrade. First, you absolutely must divide your area into an even number of chunks, basically creating pairs of intervals, just like the first and second chunk you're looking at here. Why? Because of the unique shape we're going to build right across those chunks.
Okay, here is where the absolute magic happens. By taking those two intervals side by side, we get exactly 3 distinct points on the curve: the left edge, the middle, and the right edge. Now, if you remember from basic algebra, it takes exactly 3 points to define a parabola. So, instead of drawing a straight, rigid line, Simpson's rule essentially drapes a quadratic parabola perfectly over those 3 points. And because parabolas naturally curve, they hug the actual swooping shape of the function incredibly well. That pesky error gap we talked about earlier, it practically disappears entirely. Let's look at the hard data comparing these two, because it's pretty mind-blowing. With the trapezoidal rule's linear approximation, the error drops inversely proportional to the square of your intervals, or n squared. Okay, not bad. But with Simpson's parabolic approximation, the error drops proportional to n to the fourth power. Guys, that is an exponential leap in accuracy. Think about it. Doubling your intervals in the trapezoidal rule makes the error 4 times smaller, but doubling them in Simpson's rule, it makes the error 16 times smaller.
All right, theory is great and all, but let's actually put this to a real-world test in Section 5, the speed test. Let's watch an algorithm race.
We set up an incredibly high-stakes computational race. We ran a complex integral, and we were aiming for a very specific, highly precise decimal value, 2.392576026. Now, spoiler alert, both methods did eventually reach the exact same highly accurate number. But check out what it actually took for each of them to get there.
Over 10 million intervals. That is the massive, massive amount of iterations the straight-line trapezoidal rule required just to hit our target accuracy. Meanwhile, the parabolic Simpson's rule, it achieved the exact same precision in just 2.6 million intervals. By simply changing the shape of our geometric approximation from a flat line to a naturally hugging curve, we saved the computer nearly 8 million calculations. That is the absolute definition of working smarter, not harder.
But hold on, what if we could work even smarter than that? Let's move to our final stop, Section 6, Gaussian quadrature. If you thought Simpson's rule was an upgrade, Gaussian quadrature is a complete paradigm shift. Up until right now, whether we were using rectangles or trapezoids or parabolas, we always chopped our area into equally spaced, perfectly uniform chunks. Gaussian quadrature asks, well, what if we just don't? This method strategically shifts the evaluation points, the nodes themselves, away from equal spacing. By perfectly placing these specific points at the roots of complex functions called Legendre polynomials, we essentially squeeze out maximum algebraic accuracy, achieving an order of 2n-1 precision. It is literally the ultimate optimization. It gets the most accurate result mathematically possible without adding a single ounce of extra computational weight. I want to ground us with this fantastic quote straight from our source material today, because it perfectly summarizes why all of this actually matters. Analytical math, finding those perfect, clean equations, is beautiful, but it's limited. Numerical integration, using computers to build progressively smarter geometric shapes, from basic rectangles to optimally spaced Gaussian nodes, is how modern software actually solves the truly impossible problems out there in physics, engineering, and data science. And I'm going to leave you with this thought to take away from today's explainer. If simply tweaking a straight line into a parabola can save 8 million raw calculations and slightly shifting our measurement nodes completely maxes out computer accuracy, what other invisible mathematical walls in our world can we break right through with just a slight change in perspective? Really think about that. Thank you so much for joining me on the explainer today. This was a fun one, and I'll catch you on the next one.